So we're just going to be having a brief look at kinetic theory. Kinetic theory is actually the shortest topic on your syllabus, right? It's pretty short. Alright, so we're just going to have a look at how gases react. So kinetic theory is all about gases, right? And understanding how gases relate under certain types of conditions. So the main three conditions that we look at is temperature, pressure, and degree of molarity, right? So molar concentration is what molarity is, right? So we're just going to be looking at those things and looking at how gases react under those conditions, whether or not the gas is ideal or whether or not the gas is real, right? As well as looking at Boyle's law and Charles' law, right? So I recently read the syllabus and realized that you guys don't do Gay-Lussac's law, right? But I might send some information on Gay-Lussac's law, right? I think it may help some of the physics students because I think you guys do Gay-Lussac's law, right? So after this topic, you guys should remember that we're just moving into rates of reactions with looking at exponential and logarithmic change, right? So let's just start there. What is the kinetic theory? Can anybody just let me know what they already know about the kinetic theory? What comes to mind? What do you remember from CSEC? Anybody? Okay. Nobody remembers anything about the kinetic theory? It was in section A of the CSEC syllabus, by the way. Of a person who did physics, it's in physics as well. Does anybody remember anything about the kinetic theory? You can actually read what's on the slide and then come up with something. What is the kinetic theory all about? You guys can let me know if you don't know, you know. Just try not to be just silent. All right, so nobody knows. Okay. Go ahead. You were saying something?
It has to do with states of matter and gas laws.
States of matter and gas laws? All right, for the most part,
Yeah.
yes. For the most part, actually, in your syllabus, it only has to do with that. So okay, so that's fine. So it has to do with state of matter and gas laws. Now, we'll discuss the state of matter later, but we're just gonna focus on gas. Gas is fun, all right? So we're just looking at a way in which we can measure the kinetics. And what does the kinetics refer to? It's the movement, it's the energy in which particles have. So we're looking at how pressure, volume, temperature, and concentration can affect, right, the thermodynamics of a system. And we looked at energetics yesterday when we look at thermodynamics in a sense, right? Looking at the energy in which particles have. So we're looking at the way how we can manage, right, or measure or sense the scale at which particles move or exert some type of force. So that's what the kinetic theory is all about. It's just looking at the movements and the energy and the frequency of motion of particles. That's what it's all about, right? So we have five main assumptions for the kinetic theory. The first is that gases, right, gas particles, right, are in constant and random motion. So that's the first thing. It falls under Dalton's laws, right? Well, not Dalton's law, but Dalton's principles, his postulates, right? But Dalton's postulates is something that you would look at as around your third topic in the entirety of CSEC chemistry, so you should have seen it in fourth form, right? So particles are in constant motion. Everything is made up of matter. Matter is made up of atoms. Atoms are made up of subatomic particles, and those subatomic particles are made out of waves, right? Energy fields that continue to vibrate. So, at the simplest form, reality is made out of things that continue to move. So, gas particles in and of themselves are exhibiting random motion at all times, right? The combined volume of the particles is negligible compared to the total volume in which the gases contain, right? So, what are we talking about? the combined volume of the gases or the particles itself, right, is negligible to the compared total volume of the container in which gases are. We're going to be looking at that in a simulation, right? So we're going to have that explanation of that. The particles exert no attractive or repulsive forces on each other, right? So yet again, these are assumptions, right? These are the main assumptions, right? And these are usually what we use for ideal gases, right? Particles exert no attraction or no repulsive forces on each other. Now, the first topic that we looked at in January was forces of attraction. And we learned, or we looked at or reviewed the fact that particles or matter itself always have attraction, whether it is between two separate particles or within the molecule itself. So this assumption, we already know it's false, but it is an assumption that we have to remember for ideal gas characteristics. Right? We also have collisions. Collisions between particles are completely elastic. No collision between particles are completely elastic in a sense, right? Energy is going to be transferred in some type of way, right? But sometimes, okay, it's not completely transferred, right? And it's not completely absorbed, right? So it's not completely elastic. Physics students will look at the elasticity of collisions and stuff like that a little bit more in depth, right? But for us, we just have to understand, that particles don't really react or collide in a completely elastic way. And then we have the average kinetic energy of particles is proportional to the Kelvin temperature. That is somewhat true. Somewhat true. Because as kinetic energy increases within a system, that is what temperature is. Temperature is nothing but the measure of kinetic energy of particles within a given area. That's what it is, right? Within a given volume, by the way, not an area, because that's 2D. So it has to be a volume. So we're going to be looking at that and how it applies to ideal versus real gases, right? So we have real gases. Every gas is a real gas, but we have ideal gases. So ideal gases are really just gases that follow the ideal gas law, all right? So an ideal gas is a gas that follows the ideal gas law in conditions of of constant temperature and pressure, right? Well, actually, it can be constant, right? Or it can just not be constant. But it depends on what type of temperature, right? So is it low temperature? Is it high temperature? Is it low pressure? Is it high pressure? That's something that we're gonna be looking at, right? And to do so, gases need to completely abide by the kinetic molecular theory, right? So the same things, it needs to occupy zero volume, right? So it needs to exhibit no attractive forces whatsoever, right? So these are characteristics of ideal gases, and we know that this is impossible because once it is made of something, once it's made of matter, it will take up volume, right? And once it exists within the world, it will have attractive forces. So we know that these are just ideal gases. These are assumptions. These are not true gases, right? For true gases, we'll have real gases. But here now, for the ideal gas law, right, we said that ideal gases are gases that follow the ideal gas law, which is stated here. So it explains the behavior of ideal gases. It is called the general gas equation, and we're going to be looking at the general gas equation, right? So where P is pressure, V is volume, N is the number of moles, R is the universal gas constant, and T is temperature in Kelvin specifically. So we are going to get this equation here, PV equal nRT, right? So this is the ideal gas equation, right? And most of your paper tools, you just use this. You don't actually use anything else, right? So PV equal nRT. Are there any questions or concerns? Any issues? Let me know if there are any issues. If you don't have issues, let me know that there are no issues. If you guys are ready to move on, just drop a 1 in the chat to let me know that you're ready to move on. All right, thank you. Anyone else? Everybody else is fine? Okay. So since we understand everything, we're going to try this question. Calculate the volume of 1 mole of an ideal gas at 0 degrees Celsius and 1 atmosphere pressure. Given that temperature itself at 0 degrees Celsius is 237 Kelvin, the pressure of 1 atmosphere is 101,325 pascals. 1 mole, so it's n is 1, right? And we know that the universal gas constant is always 8.31441 joules, right, per Kelvin per mole, right? So if we're gonna be setting up this now, how do we find the volume? We have PV equal nRT. Somebody transpose this real quick and tell me how you find volume. Just unmute your mic and let me know how you transpose this and what would be your answer.
You would find the volume by nRT divided by the pressure.
Okay. Okay. So we're gonna have nRT divided by the pressure. Wonderful. So nRT divided by the pressure. Right. So one thing to note as well, within the Caribbean, we tend to use kilopascals, right? So we tend to use kilopascals. Um, so we can use kilopascals for pressure, right? Your N must be in moles, of course. Your temperature must be in Kelvin, and your R always has that constant joule per Kelvin per mole, right? So once you do this, you must be able to find the volume. So can anybody just let me know what the value is for volume here? So is the value, the calculated volume of 1 mole of the ideal gas at 0 degrees Celsius at 1 atmosphere. Just let me know the value. What's the answer that you guys got? What's the answer you guys got? Waiting on the answer. Can anybody remind me of what the SI unit for pressure is? The SI unit for pressure? Hopefully you guys know what it is. Please. Nobody? Alright. The science is actually Pascal, so you guys can use Pascals for this. Alright. So I'm going to ask you guys to just complete that and let me know what the answer is. But in interest of time, I'm just gonna be moving to, well, the question is here. I can give you guys the answers in the chat, right? In the WhatsApp group. So when I complete that, then I'll send you guys the answer. All right. But in the interest of time, we're just gonna be moving on. Okay. So just keep in mind that you're using V is equal to nRT over P, right? And you have nRT and P, so you should be able to get V, all right? So let's have a look at this now. Real versus ideal. So our ideal versus real in this case. How are they different, right? So a real gas is a theoretical gas. It does not exist. No gas, right, exhibits those type of characteristics that real gas have, right? No gas follows those assumptions, right? So we're looking at the fact that an ideal gas would act perfectly, right, within these types of environmental conditions such as the temperature and the pressure, right? So as I said, it's a theoretical gas. It's governed by assumptions, right? Made for its behavior. So it's what we want gases to behave like. A perfect gas would react like an ideal gas, but no gas is truly ideal, right? So the properties of ideal gases are here. Ideal gases follow the laws, right? The gas laws at all temperatures and pressures, right? The gas molecules are solid. That doesn't make sense. Spherical particles, which do not attract or repel each other, right? The motion of these molecules is completely random, right? The particles travel in a straight line until they are hit by another particle. That is kind of correct. The collision of these particles are elastic, completely elastic, right? Meaning that no energy is lost under the collision. And we know the law of conservation of mass and energy, right? Or the law of conservation of energy specifically. Energy cannot be created nor destroyed but transferred. It's always transferred. So you can't really have a completely elastic collision like that, right? So there will be some energy transfer. So the average distance between the particles is much larger than the size of the molecules. That is true as well. That is actually true. Kinetic energy of each particle can vary, but the average kinetic energy of all particles remain constant. That's kind of not true, right? So these are the properties of ideal gases, right? And we know that ideal gases are theoretical gases, not real gases, right? For real gases, no. We're gonna be looking at this. So let me just give the examples actually. So hydrogen, oxygen, and nitrogen, and some other noble gases. Most notably, neon and xenon. Let's say neon, right? For now, most mostly neon. Neon is a good noble gas to look at it, right? So neon and helium are there, right? So these gases show behavior, right, under standard conditions, right? So the ideal gas behavior. And when you look at higher level chemistry and physics, you'll understand why they exhibit these behaviors, right? And that's because of the fact that these are inert, right? We know that they're small, they're not supposed to have a lot of reactivity or anything like that. That's what the ideal gas law really states, right? That's the properties. Now, inert gases like noble gases, right, tend not to have attractive forces that are not much, right? So it tends to react more like ideal gases. They are not ideal gases, but they show ideal gas behavior in some cases, right? It's very, very close to ideal gases, right? But ideal gases do not exist. Okay? A real gas now is a gas that does not behave according to the assumptions of the kinetic molecular theory. So it doesn't subscribe to the kinetic theory. That's all it is. Alright? So it's regular gases that you will encounter everywhere, right? It's gases that exist in the fluid that you are in right now, because the atmosphere is a fluid. Just like how water is a fluid, it's just that the fluid of the atmosphere is spaced out more than water. Right? So it's just that, right? So those gases floating around, right, are what we call real gases, right? So any gas that exists in reality is a real gas. So some gases come close to ideal gas behavior, like the halogens, some of the halogens, and well, the gaseous halogens, and the noble gases, some of the chalcogens and the pnictogens, right? Meaning we're talking about group 15, group 16, group 17, and group 18, right? Some of those gases, right, tend to react like or behave like ideal gases, but none of them are perfectly ideal, right? Why is this, right? This is because all gases found in the environment are examples of real gases, right? All of them. So even hydrogen, oxygen, nitrogen that behave, right, like ideal gases actually react like real gases. They are real gases, right? At low temperatures and high pressures, right? That's one thing that you need to note as well. Low temperatures and high pressures is where we have the deviation from ideal gas characteristics, right? Please note it, right? Get it tattooed somewhere. Put it on your fridge. Tell your mom, tell a friend, right? Low temperature, high pressure, right? Because this will be on your paper one and it might be on your paper two, but definitely it's on your paper one. There's no telling, right? There's no telling me that this is not coming on your paper one. It will come, right? So please remember that ideal gas deviation, or ideal gases deviate from ideal gas behavior under low pressures and high temperatures, right? Please remember that. So don't mix it up. Because if you put high temperature and low pressure, you already lose the race. There's no way you're getting a one, because after you make like a serious blunder like that, then it gives the examiner a feeling that the rest of the question don't answer properly because your actual principle doesn't make sense, right? So just try to remember that principle: low temperatures and high pressures, right? So that is where it deviates from ideal gas characteristics, right? And this is why we can liquefy gases, but we're going to look at the liquefaction of gases, right, and the liquefaction of stuff in higher level chemistry. But I'm going to explore it in module 3, right? So real gas properties, gases are made up of matter, atoms and molecules, which are always having some amount of force of attraction or repulsion. We know that, right? Atoms and molecules can never be point sized. So what the ideal gas properties we're talking about is that the ideal gases are completely solid and circular, right? Gases, right? So they're tiny particles that are really, really small in comparison to the rest of the volume. That is not true because atoms and molecules can never be point sized like that. It can never be that small, right? As they will always occupy some amount of volume, right? And under some conditions of high pressure and low temperature, the size of the atoms or molecules can no longer be considered negligible, right? As compared to the distance between the particles, because they will actually, change, right, based off of temperature and pressure. If it changes based off of pressure, that is Charles' law. If it changes based off of wait, if it changes based off of temperature, that's Charles' law. If it changes based off of pressure, it is Boyle's law. All right. So we're gonna be looking at that. Okay. So these are just the similarities between real gases and ideal gases. Some of the ideal gas assumptions are true for real gases as well. So these are some here, right? In some way, right? And then we have the differences between them. Okay. I think there's one error right here. I'm not sure if anybody can see the error. All right. I'm going to. Not sure if you guys can see the error there. But I want you guys to screenshot it and we're going to go through that. All right. So we can go through it at the end and speak about the last thing in this table. All right. So we're going to look at it. But the conditions that govern ideal gas behavior, right? So the conditions specifically, if we say that ideal gas behavior deviates, right? So we're saying that it deviates at low temperature, right, and high pressure. The best conditions for ideal gas behavior would be somewhat of a higher temperature and a lower pressure. But the real thing actually happening here now is the fact that ideal gas law actually states that it occurs like ideal gas at any temperature and pressure. So like, not really. So this wouldn't really apply really, but this is the best condition to really put on to our noble gases, etc., for them to display ideal gas characteristics, right? While with low temperature and low pressure, sorry about that, low temperature and high pressure, they would react like real gases, right? So it's just differences. So this is where they diverge, right? So they diverge here, right? And then this is where they stay true. To be really honest, we don't really go that in depth with kinetic theory in chemistry. That's why I'm just going through the main things and I reiterate the main things a lot, right? So the divergence, right, from ideal gas behavior is something that you need to know because that would be on your paper one, right? Everything else, I've not actually seen Boyle's law and Charles' law in a chemistry paper since like early 2000s. So hopefully it doesn't come this year. But keep like surprises, right? And I know that you guys love surprises as well, so you might want to learn Boyle's law and Charles' law, right? So Boyle's law now is a little bit interesting, but we're gonna be looking at this. Let's stop this right here. We're gonna be looking at this actually, all right? We're gonna be looking at it through the eyes or the lens of a simulation. So we want to derive it, right? I want you guys to derive the law specifically. All constant. I want its temperature to all constant though. All right, give me one moment. Oh. Okay. All right, so give me one moment. Let me just restart this thing. Okay, so can you guys see my screen? Let me know when you can see it now.
Yeah.
All right. So looking at ideal gas equations, right? So we're going to be deriving the different laws. So if we were to keep volume constant, so looking at what we're holding constant, we're keeping the volume of a system constant, all right? We're going to be looking at this in collision. in collision theory as well for rates of reactions, right? So if we were to input a certain amount of particles, say an n amount of particles within a volume specifically, right? These particles are always in constant motion, as you can see, right? And they give off certain amount of pressure here measured in atmospheres. We can measure it in kilopascals there, right? And what the pressure is just the force exerted when a particle hits the surface of a container. That's what it is, right? So if nothing is in a container, we know that the container would actually collapse on itself, right? The only reason why, for example, water bottles stay upright, the only reason why like water bottles stay upright is because gaseous particles constantly hit the surface. That's the why containers stay like that. So it's the force that they exert on the container itself. So each time a ball here hits the container, it affects the pressure, and the pressure is always fluctuating. All right. So it's something like that. So if we were to keep the volume constant, right, but increase the temperature, right, what do we see happening to the pressure?
It increased, sir.
It increases, right? So if we hold volume as the independent variable, right? So volume remains constant per se, and we have temperature increasing as you go up on the y-axis, right? We're going to have a direct proportionality being created. All right, so we have that as well, and since it's directly proportional, if we decrease the temperature, then the pressure should also decrease, and the pressure is decreasing. All right, so everybody understood that so far?
Yes, sir.
Okay,
Yeah.
so at a constant volume, right? At a constant volume, as temperature increases, pressure increases, right? And it has to be at a constant number of moles as well. Just keep that in mind, right? And as temperature decreases, then pressure would decrease as well, directly proportional, right? Let's say that temperature remains constant, right? If temperature remains constant and we decrease the volume of the container, right? So the pressure is now at 426 kilopascals. If we decrease the volume, what happens to the pressure? Increase or decrease? It was at 426 before. What happens now? Constant pressure, constant temperature, So the temperature is at 215 Kelvin here. And before the pressure was at 426. Now it's at around 600, fluctuating between 600 and 700 kilopascals. So if temperature remains constant and volume decreases, pressure increases, right? If volume increases, pressure decreases, right? That's all we're supposed to look at, the relationship between the variables. Are you guys following so far?
Yeah.
All right. So it's just something like that. Okay. So just looking at something like that. So it's the same type of thing that we're looking at for the different gas laws. All right. So if we're looking at something like because that's where the gas laws come from, right? Just investigating those type of stuff, right? So for Boyle's law specifically, all right, it says here that Boyle's law is a gas law which states that the pressure exerted by a gas, right, of a given mass kept at a constant temperature is inversely proportional to the volume occupied by it, right? So what is this saying? It's inversely proportional. So we're saying that the pressure, so P is inversely proportional to V. All right, so that's what we're saying. So if we're supposed to provide that on a graph, right, we'd have to have 1 over P and the volume here changing, right, and it would be inversely proportional, all right, there. So if it was just a graph of V against P and not 1 over P, then it would be that way, because that would be the inverse of the graph, right? So we just have to look at the relationship between pressure and volume, inversely proportional. So P alpha 1 over V, that is the relationship that is displayed on Boyle's law, right? So usually it's described as a more of a curve, and let's look at the curve here, right? So we have pressure and volume like this, right? So in this case, now we have pressure on this volume. So this is pressure against volume. You can plot volume against pressure, right? Depending on what's happening. But in this case, right, we have pressure against volume, right? So therefore, right, as you can see, if volume increases, right, then the pressure will steeply decrease, right? And we saw that in the simulation, all right? So let's go back to the simulation briefly, all right, and then look at it. And then after we just have to look at Charles' law, all right? And then we just move on into any questions that you guys have, all right? So what we're saying now, what was Boyle's law again? Just remind me, what is kept constant?
Temperature.
So temperature is kept constant here, right? And what we're saying is that the volume is inversely proportional. So what we're saying is that if we decrease the volume here, then pressure increases. So that's inversely proportional. If we increase the volume, then pressure decreases. So this is Boyle's law. Alright? So that is that. Boyle actually didn't invent the law, by the way. He stole it, all right? But you know, he's European, so we'll give him a apply. All right? So that's how it works there. So it's just inverse proportionality. All right? So what does Charles' law say now? Because I know you guys did this before in class. It's just a review, actually, because I know you guys have understood this already. All right? So what does Charles' law state now? Charles' law states that the volume of an ideal gas is directly proportional to the absolute temperature, right, at a constant pressure. So we need to keep pressure constant, right? And what we're saying is that the volume would actually change, right, due to the absolute temperature. The absolute temperature will change due to the volume, all right? So let me see if I can display that on the program, actually, because constant pressure. Okay, so let's see that. So let's try to keep pressure constant. Hold on, let me get to the thing. Give me one moment. All right, so pressure has to remain constant, right? So if we increase the temperature, oh no, crazy stuff. Okay, so let's have it here, right? So what we're saying now is that if we increase the temperature, volume should increase, right? So if we increase temperature on something, it expands, right? And if we decrease, it shrinks. So if we cool the substance, it should actually decrease. If we increase the heat, it should actually expand. So let's keep pressure constant, all right? So if we heat, volume increases. If we cool, volume decreases. And this is Charles' law. So heat, the volume expands, right? And if we cool, the volume retracts. Everybody seeing that?
Yeah.
All right. So if we heat the substance, the volume will expand, and if we cool the substance, volume retracts. All right. So that's what it's really about. Okay. So let's get back to the PowerPoint. All right. If there are any questions, you guys can let me know. By the way. All right, give me one moment. No. Give me one moment, guys. All right, so let me just kill this program real quick. Okay, so back to you guys now. All right, so looking at this now. Charles' law, right? So Charles' law states that the volume of an ideal gas is directly proportional to the absolute temperature, right? So looking at this would be the display of Charles' law, right? Directly proportional. So volume is directly proportional to the absolute temperature, right? So, and you know, absolute temperature is Kelvin. We don't use degrees Celsius in science, all right? Degrees Celsius leads to weird stuff happening. So use absolute temperature at all times, okay? And note that your absolute temperature can't be zero. That don't make any sense, right? It is impossible for your absolute temperature to be zero. Only God alone can make absolute temperature zero. Why it can't be zero is because molecules are in constant motion always. If Kelvin was zero, that means that molecules would stop moving, and that don't make no sense, right? There theoretically it can reach zero, but we'll have to discuss that in like astronomy and cosmology, right? In physics, right? But right now it's fine. So temperature is directly proportional to volume. That's Charles' law. All right. Any questions? Any questions?
No.
All right. So I did say that this shouldn't take like it's kinetic theory. It shouldn't take long. It shouldn't take long at all. Right. I did say it's gonna take like around 45 minutes, and it's actually 41 minutes so far. So we actually completed it early. Alright. It's actually that's it. There's nothing else about the topic. And I'm going to send a PowerPoint for you guys to have. Alright. So